Today's lesson is over how many solutions does my system have? Your learning target says I can determine the number of solutions a system of equations has. Let's look at this system. We have y equals 3x minus 2 and negative 3x plus y equals negative 2. I have three options. I can graph it, I can substitute, or I can eliminate. I'm leaning towards substitution because I know what y equals. So that means I can recopy this bottom equation, and instead of putting a y, I'm going to put what y equals. It equals 3x minus 2. And then the rest of the equation remains the same. Let's combine our like terms. That leaves us with 0 x's. That's gone. So negative 2 equals negative 2. That will always be the case. It doesn't matter what x equals. It will always work out. And because it doesn't matter what x equals, you will end up with what in essence is an identity property. There is an infinite number of solutions. There is an infinite number of solutions because no matter what value you give x, the equations will always be true. If you had graphed this, what you would find is that one line would lie directly on top of the other line. Therefore, you would have an infinite number of solutions. All right, here's another system. I think I'm going to go for substitution again. It just seems easy for me when I see what one of the variables equals. So I'm just going to recopy this bottom equation. But instead of putting a y right here, I'm going to put what y equals. Half an x plus 5 halves. And then just finish off my equation. And here's where some algebra is going to come into play. I'm going to have to distribute. This is actually, let me change this to a negative 2 because I think it's a little bit easier for us to see. So negative 2 times a half is negative 1x, and negative 2 times 5 halves is negative 5 equals 7. If I combine these like terms, a positive x and a negative x, that makes 0. And so what I'm left with is something kind of weird. Negative 5 equals positive 7. That can't be. And so what happens here is I have no solution. It doesn't matter what I put in for x. So because no matter what value I give x, what value my equation will never work out. If you had graphed this, what you would find is you would have parallel lines. So parallel lines here. They are never going to touch, so you have no solution. Finally, let's take a peek at this system. I'm going to use my tried and true. I know what y equals, so I can substitute into this bottom equation. So instead of a y, I'm going to put 3x's plus 4, and then I'm just going to recopy the 2x and the 8. I'm going to distribute. That's 6 x's and 8 plus the 2 x's So I have 8x's if I combine my like terms, and an 8 on one side will equal 8 on the other. Two-step equation, subtract 8 from both sides. 8x's is worth 0. The only way for that to work is if x was 0. So I think I have the beginning of an ordered pair. So my next step is to put a 0 in either equation, but I'm going to put it in right here. I'm going to put a 0 in for the x. So y equals 3 times 0, or 0, plus 4. So y would be 4. I have one solution. So if I were to graph this, my lines would intersect in one location. So when you are solving systems, you have three options for your solutions. You can have no solution, an infinite number of solutions, or one solution. And so we have to figure out which is which. So on this slide, we're talking about no solution. And the question is, how would you be able to tell there would be no solution to a system just by looking at the equations? So a system would have no solution if our lines were parallel to each other. So let's say our system, the first equation was this, the second equation was that. These slopes, we've talked about how the slopes of parallel lines have to be the same. So if you have two equations in slope-intercept form, and the slope is the same, you are going to have parallel lines and no solution. So what about infinite solutions? How would you be able to tell there would be an infinite number of solutions just by looking at the equations? Well, you're going to want them to be in slope-intercept form. And when you look at them, they will be identical to each other. If they are identical, the first line would graph, and then the second one would graph directly on top of it, or as directly as I can do with my pen. And then you would have an infinite number of solutions. All right, I want you to try these three in your notebook, solve them, figure out how many solutions you have. So you're going to pause me while you work, and then you're going to come back for checking. All right, so here's my work. Notice on this first one I used substitution. I took what y equals and I put it in right there. I distributed, I solved, and when I got done, 4 equaled 5. Hey, that can't ever be. It doesn't matter what you put in for your x and your y, it's never going to work. There is no solution there. If I had put them in both slope-intercept form, I would have found out they have the same slope, so they are parallel lines. Middle example, I actually doubled this second equation, and I used elimination this time. So I left my first equation, I doubled my second, which made my y's disappear. I solved for x, I solved for y. I have one solution, so my two lines are going to intersect in one location. On my yellow example, I actually used elimination again. I doubled everything. I'm sorry, I didn't double it. I took it times -2. So I took everything on that top equation times -2. I left my bottom equation, and that made my y's cancel. Whoops, let me use yellow. My y's canceled, but guess what? So did my x's, and so did my constants. Everything canceled, so I had 0 on one side and 0 on the other. So in this case, everything I put in for x and y will always work. I'm going to have an infinite number of solutions. If I had graphed this, one line would be directly on top of the other line. Or alternatively, if I'd used algebra to put them in slope-intercept form, they would be identical to each other. So in your notebook, I want you to write a lesson summary. Explain what you learned today. How many solutions can a system have, and how do you know? What do the lines look like that create the different types of solutions?